Last week we had a very nice discussion about your work.
Yes.
Yeah.
So maybe a request. It's better you project so that we see.
Who projects? You want me to project?
I don't know whether I can share this one.
You should be able to project on your end.
If you go to the box with an arrow inside, it allows you to share.
Device setting.
Yeah, you see the box with an arrow inside?
Yes.
You click on it, and it will give you options of either sharing our desktop windows or now we can see it. You can see it.
You can see it, eh?
Yes.
Yes, I can see that.
Okay. So for last week, we had a number of corrections. The first one was about the equations. Can you hear?
Yes, I can hear you.
Yes, I can hear you. I've also muted my microphone so that we only listen to you. Thank you.
So the equations was to redo the equations so that it's all in one format. So what I did, for example, yes, you remember. So I put them in because most of them I just wrote in word form, in word format. So I put them in equation mode. I think nearly all of them.
Okay, while you're at that equation, 3.2.
Yes, 3.2, yes.
The half should be subscript. That's the half value layer.
Yeah, the half value layer, yes, should be.
Yeah, so the half should be subscript.
Yes. I've noted. Let me just show you a few more so that you can see.
Although you can actually correct that right away. Unless it is not word.
No, it's word, but I'm on sharing mode, so I have to. Once I note in my book, it'll be easier for me to change. For example, this is the same.
Please go back to that diagram. I really like your diagrams. The before this, the page before. That illustration.
Yes. So this is a new illustration to demonstrate that different material, lead, copper, and aluminium, affects attenuation, but by different rates. Because these are the attenuating material that we shall use to characterize the beam.
Okay, this is a very good diagram.
Yes.
Now the blue symbols are for lead.
Yes, the blue is for lead, yes.
And the red is for copper.
For copper, yes.
And the green is for aluminium. So lead is a better absorber of radiation, as one would expect.
Yes.
Now the legends are sort of inverted. If someone is not careful, they might think that lead is the top curve. But if someone reads the symbol next to the word lead, then they will know it's the bottom curve. So that can be a bit confusing.
Yes.
Is it possible to redo that one? You can think about it.
Yes, this one I picked from Aziz, because ideally this lead should have been here and the aluminium the other way around.
Yeah, the other way around. It's a bit confusing.
Yes.
But one has to look at the symbols carefully. Okay. Yes. If you have the measurements, you can plot this yourself.
Yes, I can. I don't have the data yet, but I can correlate. For example, at 10, I know it's around 0.3.
Okay. Okay, you can go on.
The symbols. Then For the photoelectric effect, this is a theoretical part. We have this diagram. Then some more equation. There are quite a number. Then the Compton effect. This is from the IEA 205. Then the pair production.
Okay, can we go back to the diagram showing relative predominance of the three effects?
Yes.
First,
Yeah, it is this one. 3.6.
Yes, this diagram.
Yes.
Yeah, so can you say something about this diagram? For example, when does pair production starts to dominate? At what energies?
So the pair production is for the photoelectric effect is for the lower energy. Then as you get higher, the Compton effect it takes effect. Then at the higher energy levels, the pair production.
Okay, so at what energy does pair production starts to take effect?
I think it's from around 5 MeV.
5? Theoretically, at what energy can it take place?
I'm not sure of the exact value.
Yeah, theoretically 1.022 MeV. When you have a photon in the vicinity of the nucleus,
Yes.
so the photon produces an electron-positron pair. So the minimum photon energy would be twice the rest mass energy of the electron. Rest mass energy of the electron is 511 kilo electron volts. Twice that value is 1.022 MeV. So that's the minimum energy for pair production to take place in the vicinity of a nucleus. That means in the Coulomb field of a nucleus. If you've got a Coulomb field maybe of an electron,
Yes.
then you require more energy, maybe four times rest mass energy of the electron. Okay, these are questions that are typical in an exam.
Yes.
As you prepare for the final defense, because people will check your understanding of the physics in such a diagram. Okay, you can proceed.
So,
and just to strengthen what Daktari is saying, you've already written it in your thesis, because you say very clearly that pair production is an interaction even between a photon and an atomic nucleus on condition that the incident energy is more than 1.02 MeV. So pair production involves the disappearance of photon and generates an electron-positron pair. So the fact that you've said it, and now that you are saying you do not recall, someone would wonder if you wrote this thesis yourself. Thank you.
No, I did the research and I noted it, but it's only at this particular time I could not recall it. But I remember writing it.
Yeah, such technical details, you should have them at your fingertips. It's just like asking you the price of milk or the price of bread. If you buy milk and bread every day, you know these prices. Or the price of fuel per liter. If you fuel your vehicle every day, you have an idea. So for us in physics or scientists, we work with these quantities on a daily basis. So it's important to have them in your fingertips Otherwise, if you start taking us to 5 MeV, and in your thesis you have written 1.022, then
1.02.
yeah. And you should know where the 1.02 comes from. It's twice rest mass energy of the electron. But that is only true in the Coulombic field of the nucleus. If you take a Coulombic field of an electron, you can calculate it, and you'll realize that you require more than 1.022 MeV. Thank you. You can proceed.
Yes, actually, I wrote it to 1.02, not 1.5 as I said.
Yes, that is correct.
So this is about attenuation. Also, there was some corrections. Then this is a new diagram of the same material, copper, aluminium, and tin. So, but in this case, now you're varying the voltage from 40 to 120. The effect is, as you can see, it's not as much as in comparison to the other one.
Okay.
So again, new diagram for the lead, iron, copper, and aluminium, different material, subjected to current. The effect is nearly the same for the same material, for both for lead, as you can see, the blue, and for 100 milliamps is nearly the same. So this is the traceability for the field. It starts with the reference field, which is calibrated. Then we go to the particular air camera. Then we use the air camera to calibrate the equipment. So it shows the traceability from the reference to the air camera and eventually to the calibration of the equipment. So this is a half value layer. This is also a new illustration. So half value layer is the amount of material that will take to reduce the original intensity to half. Then the second half value layer is amount of material that will reduce or attenuate the original intensity to a quarter. So I demonstrate how I get the half value layer and the second half value layer. Later in the practical, I'll show how the values that I got from this experiment. Can you hear me? Hello?
Yes, we can hear you, and I'm following very well.
Okay.
Go on.
So this is the formula for the second half value layer. Is
let's see the figure caption for that diagram.
Determination of the first half value layer and the second half value layer. It's a problem here. It's a mistake.
Okay, you can correct that one.
Yes, of the measured air camera.
Okay. So D is in millimeters.
Yes, D is in millimeter. Thickness of the material.
Okay. Fine. Let's go ahead. we can proceed.
Okay. So this is the homogeneity coefficient. It's the ratio of the first half value layer and the second half value layer. So the specification says it should be between 0 and 1. So later on, you'll see the values I got from this homogeneity coefficient. Then the filtration. You requested that I send the literature about this. I think I sent within the week. So this is from Josella. It illustrates how different material affects, how different properties of attenuation material is affected by the photon energy. So this will inform how we select the material for attenuation. So this is the air camera, and the absorb dose for calibration of the survey meter. So then the beam quality specification, the cavity theory, so this is a calibration factor. So these are the requirement, the expectation of the results from the IAEA 2000. So the values that I should get should be almost close to this. So I'll do the results will be compared to these results. So after calibration, this is the formula for a correction. First, we correct the pressure and temperature. Then correction factor for the chamber, for the air pressure, for the reading itself, and for the calibration factor. So this formula is applied later on. Then this is a reference standard, the Immersion Chamber that we are using in the lab. So so this is how the chamber works. Basically, it's an air chamber, so electron moves as you irradiate. Then this is the readings are taken from the movement of the electrons. This is the X-ray tube. The electron comes from the coil through a thermonic emission. It hits the target, which is tungsten in this case. Then you get the X-ray. So for materials, this is a materials and method. We didn't have a lot of corrections here, but in this part, it illustrates the method that I'm using to get the results. So the first one is the correction of influence quantities. This is a formula for correction of temperature and pressure. Then this is the diagram. This is the X-ray. These are the filters. Then this is a chamber. Then this is a monitor chamber. Then this is where I place the attenuator material for the half value layer. Then finally, the chamber is here that goes to the electrometer. So for the K-air, the measurement is from the electrometer. It's corrected pressure and temperature. Then I take into consideration the calibration factor. So with this formula, we get the quality of the beam. So for the beam flatness, is the area on the left-hand side, I subtract area on the right-hand side, then I divide area on the left plus area on the right. So for the uncertainty of measurement, I group them into two. Those that I could measure, type A, and type P. These are the ones that I got from the literature. So the total uncertainty is a combination of the one that is measured. Then I take into consideration the one that is I got from the literature. So these are the results. I think this is last week. This is where we spent a lot of time.
Last week we also discussed systematic uncertainties.
Yes, systematic. Yes.
Do you recall the discussion that we had?
Yes.
Maybe for the benefit, again, you can remind us what we discussed and whether it is applicable and whether you could do it. Systematic uncertainty.
Yes. So for last time, systematic is it is for the one for the experimental data. So if you take, for example, 10 data, then you see the deviation. So that deviation is what brings the systematic error. I think that was a discussion.
Well, if you take repeated measurements.
Repeated measurements, that's the correct word.
If you take repeated measurements
yes,
on the same settings of your instrumentation, that gives you statistical uncertainties. However, if you vary your measurements, for example, you set your KV to, let's say, 50, but the instrument does not give you 50 exactly kilovolts. So if you want to determine the systematic uncertainty, you vary the KV, maybe plus or minus a certain percentage.
Yes.
And then you take the measurements. So that gives you some idea of systematic uncertainty in your final readings. I don't know if that makes sense to you.
Yes. For example, if you set it at 50, then you get 47.
Yes.
So the difference is you adjust to get the exact value that you're aiming at.
Yes.
Yes.
So that can be one way of checking systematic uncertainties. There are many ways of doing it, but that can be one way. And would it be possible, maybe in future, not within the scope of this work, in future, for your own documentation of your facility at KEBS, to carry out a systematic uncertainty evaluation of your facility? Would that be something you can do?
Yes, this is something I can look at. Actually, I can try.
Do you still have?
Actually, it would be interesting for the Kenya Bureau Secondary Standard Dosimetry Lab, because the systematic uncertainties, they arise from the uncertainties associated with the nature of the measurement apparatus, assumptions made by the experimenter, or the model used to make inferences based on the observed data. So there are those three issues, the nature of the measurement apparatus, let's say that the chamber you have, which you use, the assumption made by the experimenter, the way you measure is not the way I will measure, is not the way Daktari will measure.
Yes.
Yeah. So if you can have different people using the same measurement apparatus, you can get how each experimenter is coming up with his or her results. And then the last one is the model used to make the inferences based on the observed data. But that is not for this work. I thank you.
Yes.
Yeah, I'm in agreement. That is beyond the scope of your work.
Yes.
These are just ideas. You can capture them maybe as discussion towards the end of your thesis, as part of recommendations for future work.
Yes. The one from the nature of the experiment, the other one is for the assumption, and the last one is about the model.
Yeah, so an idea of systematic uncertainties, it can be in the discussion towards the end of your work as possibilities for future work.
Okay.
And as Dr. has said, this could be of interest to the Bureau, Kenya Bureau of Standards.
Yes,
So
yes.
that you've got some facility and you have an estimate of both statistical and systematic uncertainties.
Yes.
And as we discussed last week, this is a whole area of work, and it can be very, very elaborate.
Sure.
Okay, let's move on. So for now, we are satisfied with the uncertainties the way you have treated them. Is okay.
Okay. So these are the results. So the first experiment was about the leakage. This is before any radiation. We want to test how good is our setup. So that whatever value we get after irradiation, we can subtract the leakage. So this is one form of an error. So in this case, I took 10 readings with an electrometer. So these are the value. Basically, it was between 2.3 to 2.4. So the average is 2.29. It is in the microcoulomb. Then I get the deviation from the average, which is basically this column. Then the percentage deviation. So it was fluctuating positive and negative around the average value. So from the literature, this is okay. What is not acceptable is if the reading takes a particular pattern. Let's say, for example, it's going up throughout, or it's going down throughout the measurement. But if it's deviating or fluctuating, this is indicates a good experimental results. So in this case is a 2.29. So for the subsequent reading, whatever value I get, I take into consideration 2.29. I remove 2.29 from those values. So it was 2.29 nanocoulombs, which is extremely low.
Collins.
Yes.
The 2.29.
Yes. 2.29.
Nanocoulombs per minute.
Yes.
Does it have any diurnal variation? I mean, is it dependent on time of the day?
Ideally, it should not depend on the time of the day because we've taken into consideration the temperature and pressure. So before the measurement, I make sure the temperature is a constant. Then the pressure, I correct for pressure.
Okay.
But for the field work, it will depend on the time of the day because it affects the temperature.
Okay. Now,
Yes.
under controlled environments of temperature and pressure, you're indoors, isn't it?
Yes.
Yeah. The only way you can answer that question is actually doing these measurements, because I'm imagining the source of background to be things like muons, cosmic ray muons coming through the building.
Yes.
And they have some diurnal variation, the intensity of muons.
Yes.
Yeah, they can have some diurnal variation. That means they vary depending on the time of the day. And it would be nice for you to know this, because in examination you can be asked such a question. But that is something, again, for future work. You can just set out to check the background if it is modulated during the day, maybe high values at some point and low values at other points during the day.
Yes, again,
You
I
take a
think
24-hour measurement period.
yes.
Yeah. Do you still have interns at your lab? This is the work that your interns can do. The students,
we do have them,
that we send, the students that we send for training there, those who do the attachments, you can give them such a task to just monitor the background and investigate if there is any diurnal variation. It could be, you never know, or maybe your instrument is not sensitive to that. But it's worth to check and actually have data to verify this. But that is after your thesis.
Yes, actually, I've noted. We could check. I never thought maybe because for most of our work we take it in the morning. The only thing we take in consideration is the temperature. But now, the way you said, you can also investigate and see the time.
Yeah, like now, maybe the lab is not very busy.
Yes.
You could just set out to measure background and check the levels at different times of the day. And then you'll be able to establish whether there is any diurnal variation, maybe between different times of the day and night, if there's any variation. Okay, thank you.
Okay. So one of the requirements is that it should not fluctuate. It should be within plus minus 5%. So in most cases, if this is not achieved, we check the temperature, whether the room has stabilized enough, or we give it more time for the conditions to stabilize. So this was the first experiment, the effect of distance on the X-ray intensity. So here we vary the distance and we take the measurement using the chamber. So these are the distance in centimeter. As the detector moves away from the source, the intensity drops. So this is the inverse square law. Which was in the theory. It obeys 1 over d squared.
So the distance is in centimeters.
The distance is in centimeters.
Okay.
Distance is centimeter, because the X-ray source is not like cesium. It cannot. The intensity varies greatly. So the maximum distance is about maybe 300 centimeters.
Okay. Okay.
Yes. So this is a new diagram, the fit parameter. These are the measured readings, then are fitted using Origin Pro, and these are the results. So the model and the equation. Then I discuss about the parameters. So the second experiment was the effect of attenuator material thickness on the intensity. So in this case is copper. These are in millimeters thickness. So I vary from 0.2 all the way to 0.7. The purity is about 99.99%. Very pure material. So these are the results.
So the charge deposited is the charge deposited in picocurie per minute.
Yes, actually it should be the kinetic energy.
Okay, so this is a measured quantity, huh?
This is a measured quantity, yes. So this is
Okay.
without.
Do you have estimates of the uncertainties in the measurements? For
Yes,
example, at 0.2 millimeters, you are reporting 176.5.
Yes,
is it absolute or it is plus or minus plus or minus some uncertainty?
It is a plus minus 5%.
5%.
Yes, but
For all of them.
yeah, for all of them, because
moment. Usually,
yes.
Collins,
Yes.
when you do a measurement, just like you remember the very first table, the one where you are checking on the stability of the equipment.
Yes.
Where you are doing the ionizing radiation leakage measurements.
Yes.
You remember you did the 10 measurements.
The 10 measurement is.
Yes. So when it comes now to what you are showing us here, for example, when you have no filter, that is, you have no copper filter, I'm sure you didn't do one measurement. You did maybe 3 or even 10. How many
Actually
measurements?
10, yes.
Eh?
Actually, I did 10.
Yeah, I know that. So when you do 10, you will not get 232.5. You'll get 232.5 plus minus. Then there'll be a value, not 5%. There'll be a value, a definite value when you did the measurement without copper, when you did a measurement with 0.2, up to when you did a measurement with 0.7. There'll be different values, plus minus.
Yes.
So those are the values I think Daktari is asking. Normally you just put them there as plus minus. For example, this 232 may be 232.5 plus minus 0.6 or 1.2 or 10.5. There'll be a value, a definite value when you average those 10 values. Thank you.
Yeah, maybe I can add a column for uncertainty for all these values, because I have the data. So
no, you don't need to add a column. What you do, the way you have that 232.5, then you have plus minus.
Plus minus.
Yes, and then that value you got when you average those, because when you average those 10, you got now 232.5. Am I communicating? Yeah. But maybe the first measurement was 233, another measurement was maybe 234. Are we together?
Yes. Your point is I should add the deviation for each and every.
Correct. Yes.
Yes. Yes.
You don't need another column. You just add plus minus.
Yes. Yes.
You know that symbol of plus minus?
Yes.
Yes. Instead of saying that they were 5%, 5% is being too simplistic.
So I will put a plus minus maybe later there for each and every result.
You did the measurement, so you have the data.
Yes, I have the data. Yes.
Please continue.
Okay. So this is the same.
So you can see now when you do it schematically, the diagram now. You see you have the error bar.
Yes, the error bars.
So those error bars, they will go with that plus minus. They will not be the same. They will be different. Maybe when you did 0.7, when you used a filter of 0.7 millimeter copper, the deviation may be less, unlike when you used nothing, or the other way around. So those error bars will not be the same size. I thank you.
Okay, I agree. In this case, I put a constant error bar of 5% because all of them were just fluctuating. I just took a maximum error deviation for all the readings. Then I used a 5% for the entire plotting. But I can pick the exact value for the error and translate it to.
Okay, since you have the measurements, I think you can insert the actual errors that are observed.
Yes.
So for example, when there is no filter, it is 232, another reading of 235, maybe another reading of 228. So those are the readings you report, the average value plus or minus the uncertainty. Okay.
So it's the same. So the second, the third experiment was on the up-value layer measurement for using different material. So here I plotted for copper and aluminium. We didn't have for lead, so I just used these two. So this is for aluminium. Then if the original value was around 240, so the half is at around 120, which is 0.55 millimeter. So that's how I got the first half value layer for copper. And the same for aluminium. The original value was around 240. So half would be around, if this is the thickness, it's around 2.75 millimeter. So I discussed the reasons why mostly the density of aluminium is different from copper. So that's what makes the difference. So using that theory, the first measurement for the input.
Can you go back to the text? I've
The
noted
text
some
here.
inconsistencies. Yeah. Up again.
Okay.
There are some inconsistencies. Okay, there you are. Page 59, the top of the page 59.
Yes.
You see, when you report 0.55, those are two decimal places. And then plus or minus, you go to the third decimal. So that is inconsistent. 0.55, you need another digit on the third decimal to justify the plus or minus 0.005.
So maybe I can just round it. I can put 0. So that is the same as this one. It could just be 0.1.
No. You need to be consistent.
Basic physics now. When you start the physics laboratories, that's you're always trained on how to keep consistencies on the decimal points. I thank you. So don't round it.
Yeah. So don't round it off. You have to go back to the 0.55 and check what was the third digit.
Third digit.
On the third decimal point, what was the value? And then you bring it back. Same for the 235 plus or minus 0.1.
Okay.
Yeah, the 112.5 plus minus 0.1, that one is okay because you're consistent with the number of decimal points.
Yes.
Yeah, the next one is 2.74 plus minus 0.005. So the uncertainty is on the third decimal point, but the average value stops at the second decimal point. So that is a problem in scientific reporting.
Yes, my understanding is that the uncertainty is on the last. It's for the last value. So if it is 2.74, so it fluctuates between this 4 fluctuates between plus minus 0.005.
Yeah, but you need another digit after 4.
Yes, I need another digit. Yes. So,
yeah. So go back to where you got 2.74 and see what was that digit.
I think the problem is
on the third decimal point.
Yes.
And then now I think you can appreciate what we just discussed. Remember before you had said you just averaged with 5% deviation. So instead of averaging, now these values, if you are, let's say, to plot using these values like that, 2.74 plus minus 0.005, Now that's 0.005. If you are to do an error bar, that is the length of that particular error bar. And that particular error bar will not be the same as, for example, if you look at that one, 12.5 plus minus 0.1. Are we together? You see the two error bars will not be the same.
Yes.
Yes.
This one very small compared to.
But my point is this: when you do those error bars, these are the values you use now.
Okay.
Yeah, but take into cognition the way scientific reporting is done. If you say 0.55 plus minus 0.005, then that's 0.55. You need to take it to a third decimal place.
Okay.
Thank you.
So it's the same. So here is the first quality measurement. So for this beam quality, the ISO specify the amount of material that I should use. So I do the settings as illustrated in the previous diagram, and these are the results. For example, different thickness with no material, then I add 0.05, add 0.10, 15, and 21, so that I can see the amount it takes material to reduce it by half. So these are the result, the corrected result. These are the results that I got, but I correct pressure and temperature. So without any material, it's 471.97. Then it reduces as I add material across the beam. So these are, in this case, I got 5 readings, 389. It fluctuates. So in this case, it will be plus minus the fluctuation of these 5 readings, as you indicated earlier. So also for this one, it fluctuates according to this. Then these are the results. Again, the error bar will change because I'd put a constant factor, but now I'll see the deviation of each and every reading and put plus minus, then plot against that deviation of the error on the error bar.
Isn't it the last column, the one where you have Q?
Here, this is the final results. Yes.
Yes, so I'm asking that last column, the one which has LN.
Yes, I can use for the value. I can use any of the two.
No. What I'm asking, that very last column, what does it represent?
No, this is not the. It's not the deviation.
I'm asking, what does it represent?
This is a. So this is a semi-logarithmic scale plot.
Yes, so what about the semi-logarithmic plot?
The last column on that table, that was the question. What does it represent? I think Collins has some technical issues.
Yes.
Connectivity. So we can give him some time to see if he can log in, and we proceed with the discussion.
That's true, but you know, he's literally finished the work. It's only that
yes.
What he needs to do is read it again and again, the way you read for an exam, so that you have all the answers at the fingertip. He's coming back.
Okay.
Okay. Sorry for the internet. So the last column was is the natural log of all the attenuated material that are used.
Okay, so let's proceed from there.
That's correct. Yes.
Yes. So we are at so this was the results. So plotted against thickness against
you
the
need
thickness
to share
against.
again.
Sorry.
You need to share your screen because you left completely. Now you are back.
Sorry. Now you can see.
Yes. So you had that plot where you used the Q value so that it was coming out like an exponential fit.
Yes.
That's where you are.
Yes, this is where I am. Yes.
Yeah. Yes.
So I plotted the thickness against the corrected value. This was the measured value, but now corrected to include temperature and pressure.
Did you try plotting again the thickness with the logarithmic one?
No, I did not, but it's also possible to plot both the thickness against the logarithmic one. And it will be a straight line as on
correct,
like
yes.
previous one is. So do I continue? Or? So maybe
Please,
I can add another graph for the natural log.
No, I think you already have a graph for natural log of Q versus thickness. Yeah, so no need of another graph.
Yes. So these are the result. Basically, with no attenuator, it was around 400 and maybe 60. Then as I increase different attenuator material, it decreases. So that's for this specification on 40 kilovolts. So I've been measured and exponential fit to see the effect. So I did this for different beams for 40 kilovolts, for 80 kilovolts, because the ISO specify that we should characterize for each and every voltage range. So it's the same for 80 kilovolts. Same experiment. 5 readings for each setting and the corrected value. Then the results. That's for 80. For 120 kilovolts. Then the last one for 150 kilovolts, basically the same. Then that's the result. Then 200, which is the highest in the lab. Then so this is the final results for all the qualities. This is a tube potential. Then these are the different composition specified on the ISO 4037. Then this is the result for the first half value layer. Then I compare with the one that are specified on the by the ISO to see whether it's within the required range. Then this is the second one, range from 40 to 200. Then I do comparison with the one that is specified by the ISO 4037 for the entire range. Then this is a discussion. Then there's a graphical representation of the same. The measured.
1 minute, Collins.
Yes, yes.
Take me back to the table. Just for point of clarity, first HVL and second HVL, what do you mean by this? Is it these are two readings, or is it the first HVL and the second HVL? Am I communicating? Collins. We seem to have lost communication with Collins. Collins, are you able to hear me? Collins, are you able to hear me?
Yes. Hello. Can you hear me now? Hello?
Yes, I can hear you.
Okay, let me just load it. Internet is fluctuating. This is. Yes, this is a table.
This is the table. I was seeking clarification from you.
Yes.
I want to understand the columns where you write first HVL and second HVL. Are these readings 0.8, 0.08, and 0.90? Are these readings of the HVL?
Yes, these are the readings from the HVL.
Okay.
These are the measured ones. Then these are the one that are specified by the ISO, like guidance.
Okay.
Yes. Then this is how the different material that I use for this 40 kV quality. So the ISO specifies that I should use 0.2 millimeter of copper and 0.2 millimeter of aluminium. So for 200 kV, it's 1 millimeter thickness of lead, 3 millimeter of tin and copper, and I don't use aluminium in this case. So this is what I've plotted just to give a representation. So the red is the ISO one, then this is measured. So the deviation is there, but within the required specification. This is for the second half value layer. This is for 80 kilovolts quality. Same for 120 kilovolts, 150, and eventually to 200. So this is how we characterize the beam using a half value layer measurement. So with this, the second way, the second step is to carry out the homogeneity coefficient. So this is a comparison I did for.
Before you go for that,
yes.
Project the graph again.
Here.
Yes, this graph.
Yes.
Now let's discuss the physics here. Is it what you expect from physics when you increase the voltage from 40 to 200? The half value layer increases. Is it what you expect from physics? Are you able to interpret this using physics principles?
Yes. From a principle perspective, all these should be the same, ideally. Both the value for the experiment and the practical should be the same. And as you increase the kilovolts, the half value layer should also increase. Because
clearly we can see from the measurements.
Yes.
And also from the ISO requirements. But from physics point of view, are you able to understand why the half value layer increases as you increase the voltage from 40 to 200 kilovolts?
Because this is the effect of attenuation. So this just represents the thickness of material that reduce the original intensity. Did I get it right?
Yes, yes, you're in the right direction. So basically, the higher the photon energy, the more penetrating the photons are in the material.
Yes.
And in other words, you can also say the higher the photon energy, the less the probability for interaction.
Yes, yes, yes. As you increase
So,
the energy level,
yeah,
the penetration power increases.
yeah, it penetrates more.
It
So
penetrates more.
you must have some physics understanding of this half value layer and how it varies with the kilovolts.
The kilovolts.
So when you increase the voltage, you increase the intensity of this beam, isn't it?
Yes, yes.
Yeah. Okay. So get to understand the physics and be comfortable with the physics explanation. Why the half value layer increases, because these are the kind of questions that are posed during examinations. You've got good measurements, but are you able to understand them from physics point of view?
Okay. Okay.
Okay. So you need to know the physical processes that happen in the material.
In the material, yes, yes.
Okay.
So this is the penetration power. Again, as you increase the voltage, the photon energy increases. Then eventually, the beam is more penetrating. So again, ideally, this should be the same, but the second half value layer is attenuated differently from the first half value layer. And this is because of the material that is used in this case. But another reason for this is for the low energy, the photoelectric effect is predominant at this level. Then as you increase the energy, the Compton effect is predominant in this area. So the first half value layer is a photoelectric effect, and the second value layer is Compton effect. So the deviation is affected by it's affected by the interaction process.
No. I think you're getting mixed up, Collins.
Yes.
Yeah, don't go that direction. There you're getting mixed up.
Yes.
Let's go back to the basics of your X-ray beam.
Yes.
When you increase the voltage, you're increasing the kinetic energy of the electrons that impinge on the target.
Yes.
Okay. Now the target is the same, isn't it?
The target is the same, yes.
It's a tungsten target.
It's a tungsten target for all the
Yeah.
voltage ranges.
So for all the voltage ranges, the target is the same. It's a tungsten or molybdenum or copper, whatever it is.
Yes.
So it gives the same characteristic energy of the photons. Are we in agreement?
Yes.
So when you increase the kilovolts, you're increasing the kinetic energy of the electrons that bombard the target.
The target is.
So what happens? You're only increasing the intensity of the beam. The photon energy is the same continuum with a characteristic peak of that target.
Yes.
Are we communicating up to that point?
Yes. Yes, yes, yes.
Now, the effect of increasing the kilovolts, you're just increasing the intensity. So you have more photons coming out of your X-ray unit. And if you go back to the definition of the half value layer, is the thickness of your material required to reduce the intensity of the photons by half. So the more intense your beam is, the thicker the material you need to reduce that intensity.
Yes.
I don't know if that makes sense.
Yes.
Does it make sense?
The higher the voltage,
Yes.
the higher the
intensity
material that will reduce the original by half.
Let's go step by step. You have the.
For example, at 60, you require lesser material to reduce the original intensity by half. Then, as you go higher,
yeah, because there are more photons. As you increase the voltage on your X-ray tube, what you're effectively doing is to increase the intensity, the number of photons that come out from the tube.
Correct, yes.
Yeah, because the target is the same, isn't it?
Yes, the target is the same, yes.
Target is the same. So it gives the same Bremsstrahlung continuum and a characteristic peak. So that characteristic peak is the same for that target. It does not change with the energy of the incident electrons.
Okay. I think here
So
I confused myself. Yes.
Yeah, the photons come at the same energy. It's only the intensity that increases. Now, if the intensity increases when you increase the tube voltage, that means you need a thicker material to stop these many photons that come incident on your material. So that's why the half value layer increases as you increase the tube voltage.
Okay.
Does that make sense?
Yes, as you increase the tube voltage, the intensity increases, which eventually affects the material that you need to reduce it by half.
Yes. So the tube voltage effectively increases the number of photons, the intensity of the beam.
The intensity is.
And half value layer is the thickness of your material required to reduce the intensity of the beam by half. So if you have a beam that is more intense, the half value layer must increase.
Yes.
The more intense your beam is, the thicker the material required to reduce the intensity of the beam.
Okay.
I don't know if I've been able to communicate that.
Yes.
Okay, so we can proceed.
Okay, maybe. Let me just mark it. Okay. So this is the second step. The first one is the half value layer. Then now the homogeneity coefficient. So the ISO specify that if you calculate the ratio of the first half value layer and the second half value layer, it should be within this range 0.75 to 1. So these are the experimental value for 40 kV. I got 0.392, 80, this one, 150, 0.915, 200 kV, it is 0.995. So as long as I'm within this range, then can comfortably say that the readings are within the required specifications. So then I plotted this. No, I didn't plot, but these are the final results. For homogeneity coefficient and in comparison to ISO 4037. So do I continue? Or? Hello?
Yes, you can continue.
Okay. So the last stage was on the physical property. So what I did at a distance 100 centimeter from the source, I moved the chamber across the field, in this case from 70 to 110. Then I take the value of temperature and pressure, corrected. These are the average values. Then these are the plotted the distance. But the figure that I want to show is this one. So I think there's a mix-up. This figure should come. Sorry. This was for the profile. So this is the readings of the profile from 0 to 30 across the right hand side, then 0 to 30 distance in centimeter on the left hand side. Then this was the Ka nanocoulomb in 10 seconds. Then this was a final profile.
Okay.
Yes.
Okay,
So,
you can proceed.
yes. Look, if you the way analyze this profile, I found there was a deviation of about 2 centimeter from the alignment was 2 centimeter off from the central axis beam. So the third objective for the thesis was on the KI measurements, the kinetic energy released per unit mass. So this was a background reading, the one that the first experiment, then the measured value. Then I put into account all these factors that affect the measurement, the calibration factor, pressure, temperature, the scatter. All these are found from the theory. Only one was measured, the kinetic energy released per unit mass, but all these were from the theoretical literature. So what I did, current, temperature, then the correction, then these were the readings, 1.28 nanocoulomb per minute of charge, then corrected, then this was the final value of Ka in microgray per minute. Then these are values is converted into area monitoring, because the surveyor meter is for measuring field measurement. Then these are equivalent in Roentgens. These are equivalent for the personal dosimeters. So using this value for the experimented results, I do the same for the survey meter. For the survey meter, here it is. At 40 kilovolts all the way to 150. Then these are the results for the reference for the survey meter. Then these are the deviation from 5 to 6.6. Then eventually to the calibration factor, which is a ratio of the reference standard compared to the measured reading. So here, for ideal case, it should be 1, but in this case, these are the values that I got. The average is 0.94. So this is plotted on the graph. Here it is. Just to see the survey meter reading in comparison with the reference standard. So as you increase the energy, both of them increases. It takes a pattern of the reference standard, but there's a constant deviation, which is the error. So the calibration factor.
No, it's not the error. It is now where you bring in the calibration factor, not the error. It's not an error.
Yes, actually, yes, you're right. So the calibration factor tries to correct this the reading of the survey meter. That ratio, if you multiply with any value of the reading here, it reduces it to this pattern. So it's a correction. It's a value for correcting the. I don't want to use the word error. It's a value to correct the reading here to this level, to drop the reading from up to down.
Actually, Collins, if
yes.
you remember the first box you showed us where you have the primary, then the secondary standard, then the field equipment.
Yes.
Now, the field equipment doesn't have the advantage of the secondary standard equipment. The secondary standard equipment, in addition to maintaining our standard as a country, we also compare it with the primary standard, let's say from IEA or from Paris.
Yes.
Or from Germany.
Yes.
Yes. So now so this calibration factor, when you multiply it with the value of the survey meter reading, you get the standard. So now there's traceability. And then of course the standard, of course, when you compare with the primary, you also have a similar diagram. So the traceability is assured. And now the dependability of this measurement of the survey meter is assured. I thank you.
Yes, you're correct, because now, for example, without the benefit of the reference standard, if you read this meter directly, this could be the values. But now, because of the traceability and the calibration factor, the value of the survey meter now will be corrected from here to the corrected value. So this is the traceability as explained in the previous diagram. So on the issue of calibration factor of the survey meter, so this is the different values for the calibration factor. So if this is multiplied by the correction factor, all these values will be around ideal value. But this also shows the deviation of the expected reading and the experimental results. So this was the last one, the profile. Different ranges on the left and on the right across the beam. And it eventually leads to this diagram. It was taken from 200 centimeter from the source. So this is the field size. This is very important because during calibration, all the measurement equipment should be within the profile. If it is taken outside the profile, then the equipment will be partially calibrated. So this is one of the reasons why this exercise was very important, so that we know the size of the profile to guide the calibration process. So for the lab, all our measurements should be within the central axis beam. We place all the equipment right at the center. So this was the third and the last specific objective. So I tried to analyze that profile, and I found that there was a displacement of 2 centimeter. This, I think, was an error during commissioning stage of the equipment. So lastly is uncertainty, a measurement of all the experimental work. So it is in 2 parts. The first one is on the reference standard. So as I said earlier, both type A and type B. So type A is the one that is measured. The reference value is the stability, how it fluctuates. So it's 0.30, and the reproducibility. Then for type B, these are the ones that are from the certificate or the literature. For example, 0.385 from the certificate of a calibration. The ruler that is for measuring the source distance, 0.58. The uniformity, all these are from the experiment. The conversion coefficient, this is the highest, and this is from the ISO 4437. It has the biggest contribution. So if this is summed up, it comes to 5%. So for this experiment, the total uncertainty is plus minus 5%. Then for the survey meter, for the client equipment, we pass that 5% to the client equipment. So the chamber, the 5%, the meter itself, the temperature, pressure, and all these other factors, it's almost double. It comes to around 11%. So this means the capability of the reference it's better by almost half of the client equipment. So that was the last experiment.
Okay, that is good.
Then we go to conclusions and recommendations.
So the lessons from this. So I talk about the field, the accuracy. So this is the first one. The measurement results obtained from the half value measurement are consistent with the ISO 4037, and it's therefore conclude that KEP's STL addition field is well established and meets the requirement. So all this result indicates that we met this requirement of ISO 4037. So it also demonstrates that the laboratory, through this characterization, we can use it to demonstrate our competence as a lab. That whatever we do in the dosimetry laboratory is competent enough to carry out. The results are competent enough for this work. Then the second conclusion is that through that high-value layer measurement, the range are also consistent with ISO 4037, and therefore the quantity air camera is suitable for calibration. Then the third conclusion we recommend that any equipment that is used for radiation measurement should be taken for secondary standards laboratory for calibration. In that figure, I showed the deviation of the reference standard and equipment for client. So no equipment should be read directly. Every equipment must have a calibration factor so that it can correct the readings.
Yes, and in saying that, Collins, because
yes.
you are now in conclusion,
yes,
it is always good to explain where the reasoning is coming from. So you can say something like, radiation survey meters are used to measure the presence of any radiation from radioactive sources or radiation generators such as X-ray machines, linear accelerators, etc. So now the fact that you've stated how radiation survey meters are used, then now you can say the proper calibration of these instruments is to ensure that all meters are working correctly. And that's why you did all your research. Now, so annual calibrations are required for all the type of survey meters. So that's how you conclude. I thank you.
Yes, I've noted. I'll modify.
I'll give you the recording of this. I'll give you the recording of this.
Yes, I'll be grateful. So the other conclusion was that all this equipment should be
and then also Collins,
yes.
since this is your research and it needs to have an impact, so you can also say that the calibration of ion chamber is mandatory to fulfill the legal requirement and IEA recommendations to ensure that the measurements are compatible with those made elsewhere and to assure constancy to promote customer acceptance. Thank you.
Actually, that's exactly the reason why we do this is that any measurement done in the dosimetry laboratory, that measurement should be the same as the one that is done in another country.
Yes, and also, you have to also qualify the fact that the calibration factors of ionization chamber survey meter are changing from time to time. Like the calibration factor you gave, let's say in 2015, may not be the same as 2016, 17, 18, and now we are 2020. It's a fact, that one.
Yes, it fluctuates depending on the time frame and how often the equipment is used.
And that is how now you bring out the fact that it's important to do more research, because the ionization chambers are sensitive, they are reliable, and show good energy response to X-ray and gamma radiation. They should be maintained and kept carefully in the dry cabinet if they aren't in use. Because if you do poor maintenance, you'll have scenarios where you think it is high background reading of the survey meter, you think it is due to leakage radiation, but that is for other research to do, not this one. You have to point out where the holes are in what you've done, and invite other people to continue where you've arrived. I thank you.
Yes, yes. I think you'll help me with the recording so that I will add more, a few sentences.
Yes, I'm in agreement. Those are very important points to add to your concluding remarks. Very, very important. Yeah, thank you.
So the other issue I try to bring out is that the radiation measurements are affected by the influence quantities like temperature, pressure, and humidity. So for very accurate results or precise results, the influence quantities, environmental factors should be taken into consideration.
Yeah, that is proper what you are saying.
Yes.
And also in your conclusions, because people will be wondering, especially people who are not conversant with the role of Kenya Bureau of Standards and Secondary Standard Dosimetry Laboratory in particular, they should know that the reason we calibrate the survey meters is that these calibrations are to be conducted in an isolated area and this facility where the background radiation is low. You see the way you have built your bunkers. You can't compare them where these equipments are used. And then something which also you could bring out for future for other people to work on. For example, when you are doing all these measurements, I hope you are wearing your you are wearing your dosimetry badge. You could point out that this dosimetry badge, it is electronic, but ideally, the regulator, now the Nuclear Regulatory Authority, they should be getting the doses you receive or any other worker receives. Not only you, but also the people who use these survey meters.
Yes, we are required to wear this for safety. We have to know after every experimental work, we are supposed to note the difference. So I will include the issue of safety.
Yes, but ideally, in addition to the electronic badge you are wearing, which gives you the dose after every encounter in the lab, that is after every day, you should also be having another one, which now you can read, you can wear it for, let's say, a month. Like, let's say if it was a TLD, you can have it for a month, maximum 3 months. And the readings of that one you wear for a month, they should be availed to the Nuclear Regulatory Authority.
Yes. Initially, we never used to fulfill that requirement until I think 4 months ago. Right now, we gave a contract to a third party to be monitoring our dose results. But from the perspective of the regulator, that is what is supposed to happen.
So those are things you discuss in your conclusions and recommend.
Yes.
And then I hope that you also have a survey meter which is similar to those, which is more of a reference standard, so that you can ensure if there are any unexpected changes in the exposure rates, they are identified. But if you do not have, this is again a time when you call for Kenya Bureau to acquire, like because in your experience with, for example, hospitals, you know what type of survey meter they use. So it would be good you have one similar survey meter, but the yours is a reference standard.
Yes, the one we have is quite precise. Sometimes the one we get from the field, the errors are quite, the deviations are quite high.
And what I'm pointing out is that the ones you get from the field, you should be having a similar one. For example, if it was a car and it is a Toyota, for example, Land Cruiser, even which is used in the field, you should also have a similar Toyota Land Cruiser, so that when you are seeing any unexpected changes in the exposure rates, you are able to identify from yours, and you can understand this one from outside. You know, in that spirit of systematic errors, I mean systematic uncertainty.
Yes.
Yeah, continue.
Okay. So then I try to bring out the factors that affect that contributes to uncertainty of measurement. So these are the environmental condition, the calibration factor of the reference standard, the positioning of the instrument. Like in this case, we positioned vertically. If you position it horizontally, the value changes again. So the results that are released should also indicate
So you are finished, or you are still continuing?
In the lab, we try to minimize this. The labs are quite big enough. Then also the scale readings. So then in terms of recommendations, one of the reasons for this thesis was we did intercomparison with NIST, and we got our results. So with these new changes, it could be better now when we do another comparison with NIST or another primary laboratory. Then we see how far we are, whether the results has improved or not. So that was my first recommendation. Then that would really inform whether the new measurements for the half value measurements are good enough, and because we'll get clear results of the previous results and the new results. Then I try to for research work. This was the result. The characterization was only limited to the exposure quantity of the beam. So it is recommended that the accuracy and certainty of measurement associated with the diagnostic, for example, for the ones that are used in the hospital and for treatment, can also be investigated. So the uncertainty we get in the lab, it could be better also to carry out a research work for the results that are done in the field, for example, in the medical sector, and see how good are those results. So I recommend similar work for, let's say, a CT measurement, for mammography, and also for dental applications. Basically, for all the applications that are used outside there.
So you finished?
Yes, I finished this.
Yes, so one last thing you should also point out very clearly, the issue of records. So ideally, records should be kept of each survey performed, and this should include the owner of the instrument, manufacturer's name, model number, serial number. Of course, I'm sure signatures of the individuals who performed the calibration, date of calibration, when it was performed, and the next expected calibration date. So all such records of calibration results should be kept for some period, maybe 3 years, or depending on your organization, let's say bureau, or you can recommend for nuclear regulatory authority, how long.
Yes, I agree. There's need to keep this data so that it can also give information, for example, of equipment from a particular manufacturer, whether those particular equipments have better accuracy, or we can see a consistent results of maybe a particular model, so that we can also inform even the manufacturers how their equipments are performing out here. For the data, okay, we have a weakness as KEPS. We don't sometimes we don't keep records for the people who bring these equipments, but I think this one we should. So that we can also do follow-ups.
Collins, that should come out very clearly in your recommendations, not only to the Bureau, but also to the owners of this equipment, and of course to the Nuclear Regulatory Authority. Because if all the records of calibration results are not kept for a period, then we will never be able to know the trends.
Yes.
And also, normally the results can be concluded that the ionization chamber or survey meters need to be calibrated annually and must be maintained carefully to reduce the discarded effects of the measurements. But you can never do that if you don't have records.
Yes, I agree.
So that's how
actually
we consider
because now, for example, to the regulator, this data does not reach the regulator. So I think there's a weakness there about the equipment calibrated performance.
I think that's a very important point. And it should also be taken into account in our procurement policies. Most of our institutions have procurement policies, which should also take into account calibration and regular maintenance of this kind of equipment. So if that is captured in the policies of our institutions, it would be wonderful that the records are kept properly and also shared with the regulator. Thank you.
Yes, I think I agree. That's another weakness. For example, if another institution want to buy an equipment, maybe this record can inform maybe a better equipment. How will you know this a particular equipment model or manufacturer performs better? So this could inform policy in regards to procurement.
Okay, thank you very much. It seems you have come to the end.
Yes.
Thank you very much.
Welcome.
So there are a few areas where you need to improve on the thesis. Okay, so if there is no other item, I think we are grateful for this opportunity that you have shared with us, your findings and how you are presenting them. So maybe we can take some time now to look into the areas where we have suggested corrections and areas of improvement.
Yes.
And most importantly, get to know the physics in your fingertips so that now we prepare for the examination. Thank you.
Yes, just before you leave, maybe I've noted most of the corrections. Hopefully by next week, I shall have made adjustment. Maybe we can as well review maybe next week, Friday. I think.
Yeah, that's okay. That's okay with me.
That's fine also for me.
Yes. So maybe Dr. Toma can send me the recorded version so that in case I miss something, it will be easier for me to put it in.
Yes, that I'll do. So can I stop recording, or we are still having some new information?
No, there's no new information from me.
Okay, we can stop recording. I think we have discussed exhaustively. Thank you.